As the international community continues to shy away from fossil fuel in order to keep the 1.5-degree goal at reach, more wind farms are installed across the world. Electricity from wind power increased by 800% from 2008 to 2014. Its contribution to the global energy mix increased from under 1% to 7%. At this rate, we will be seeing wind turbines around every corner of the globe. Wind turbines are very large civil infrastructures. For the onshore wind turbines, the average blade length is between 45 and 75 meters. The tower height is often twice the turbine length, from 90 to 130 meters. Tower diameter can be as wide as 3 meters, and the whole structure sits on a circular foundation poured with truckloads of concrete with 15 to 22 meter diameter. The largest onshore wind turbine can reach 180 meters tall, dwarfing the Washington Monument and the Statue of Liberty. The monstrous offshore turbine can reach as tall as 260 meters, comparable to the 77-story Chrysler Building in the New York City. As applied seismologists, we are interested in the vibrations generated from the wind turbines as well as their influences on the surrounding infrastructure and the environment in general. So let's start from the biggest moving part of the wind turbine, the rotor blade. The rotor blade is the most obvious moving component of the wind turbine. The sweep area of the rotor blade is directly proportional to the power generation and highly correlate with the wind turbine efficiency. As the wind speed increases, the blades generally rotate faster. Modern wind turbines are designed to stay motionless when the wind speed is lower than 3 meters per second, roughly 10 kilometers per hour. The blades will rotate at a constant speed if the wind speed is too high, larger than 10 meters per second or 36 kilometers per hour. This is to avoid overheating of the rotor and the generator. Blade rotation generates constant vibration energy at a rotational frequency called 1p, which could range from 0.15 to 0.3 Hz and wider, depending on the manufacturer. Since there are 3 blades, additional vibrations are generated at the blade passing frequency called 3p, 3 times the 1p frequency. Due to these constant vibrations, the turbine engineers have to design the tower such that its natural resonance frequencies do not overlap with the 1p and 3p ranges. When the wind picks up, the tower feels more vibrations from the blades, but the tower vibration at its natural frequencies increase even more and still dominate the overall vibration spectrum. To monitor vibrations from the wind turbine, sensors can be installed inside the tower. The sensing data provide information for wind turbine operation status, tower health, as well as preventive maintenance to avoid severe accidents. Vibration sensors can also be installed on the ground, making the data collection and transmission easier. This will enable monitoring of multiple wind turbines at the same time, monitoring of structure-soil interaction, and alert for any abrupt changes in the subsurface properties that may cause severe damages. That is the basics for wind turbine vibrations. To learn more, stay tuned.